So good morning, everyone. I hope you can hear me. Good morning to the people online. So this is like the third day of EAAMO and the first session of today on algorithms for allocation. And I'm very happy to introduce our first speaker, which is Roshni Sahoo, who will speak about policy learning with competing agents.
Hi, everyone. My name is Roshni, and today I'll be presenting some work called Policy Learning with Competing Agents. This is joint work with my advisor, Stefan. So decision makers often aim to learn policies for assigning treatments to people under capacity constraints. So we can think of a policy as being a mapping from the space of observed covariates X to a treatment assignment 0 or 1, where 1 denotes receiving the treatment. For example, we can think of college admissions. A college may try to learn a policy for determining which students to accept or reject, and they may be constrained because they can only accept a particular fraction of the applicant pool. We can imagine that the decision maker incurs a loss of L pi nu when assigning a treatment pi in 0 or 1 to an agent of type nu. So the decision maker's goal in this scenario is to minimize the overall population policy loss while satisfying their capacity constraint. We can think of the policy loss of the decision maker as the loss the decision maker incurs when deploying a policy pi over a population of agents with types following some distribution. Furthermore, we can think of the decision maker's capacity constraint as limiting them to only allocate treatment to a fraction 1 minus q of the population. Standard policy learning approaches assume that the data we observe is exogenous. What this means is that the data we observe does not depend on the policy we deploy. However, if we're trying to deploy a policy that affects people, people may know about the policy and behave strategically to get a more desirable outcome. For example, in our instance of college admissions, we can imagine that a student, knowing that extracurriculars are really important for getting into college, may sign up for more clubs to improve their chances of admission. So to understand the challenges that arise in this setting where we have capacity constraints and strategic behavior, we can think of the example of college admissions in a little bit more detail. So we can imagine that last year's college admissions policy is known to the students. So basically this policy from last year depends on policy parameters beta and S, where beta is essentially a selection criteria that weights the observed covariates, and S is the threshold for acceptance. So agents that score above the threshold S are accepted to the college. This year, because students have known about last year's previous policy, they'll respond to the previous policy. So we can imagine that the students' reported covariates depend on the policy parameters from the previous year. So the covariates they'll report are X, beta, S, nu, where beta and S are the policy parameters from last year, and nu is their private type that determines their behavior. As a result, we can imagine that a distribution over scores is induced by their strategic behavior. So this distribution is denoted as P beta S for the dependence on last year's policy parameters. Now, because of the capacity constraint of the college and the strategic behavior, the threshold for admission will change. So basically, as I mentioned before, the decision maker can only accept a fraction 1 minus q of the population. As a result, the threshold for acceptance will now be set to the qth quantile of the score distribution, or qp beta s. Here we see that the combination of strategic behavior and the capacity constraint leads to competition. So basically, we can imagine that the threshold for acceptance may change over time and possibly even increase. And we can kind of see that finding beta that minimizes the policy loss in the presence of this competition is hard. The first reason why it's hard is because students are reacting strategically to the college's previous policy. So this means the covariates they report have some dependence on the policy that was reported in the previous year. Furthermore, the capacity constraint causes the threshold of the college's realized policy to depend on students' strategic behavior. So basically, the threshold for acceptance is going to change in the next year as a result of the strategic behavior. And it would be infeasible for the decision maker to be as reactive as the students and react to all of these oscillations in competition that are going to occur over time. As a result, we propose an approach for minimizing the overall policy loss based on equilibrium modeling. So we can let S beta be the equilibrium threshold induced by the fixed selection criteria beta. This means that S beta satisfies the fixed point equation S equals QP beta S, which basically means that the threshold for acceptance is fixed. In our work, we propose to find beta that minimizes the equilibrium policy loss. We can think of the equilibrium policy loss as the policy loss that is incurred under a fixed selection criteria beta when the threshold is set to be the equilibrium threshold. The reason why we take this approach is because there's no oscillations in the level of competition at equilibrium. The threshold for acceptance will be fixed at an equilibrium level. So we can imagine the competition is at equilibrium. Furthermore, we can think about optimizing the equilibrium policy loss as optimizing for the long-term behavior of the system if we eventually believe that the system will reach equilibrium. The main contributions of our work include a model for treatment assignment in the presence of competition, conditions for the existence and uniqueness of equilibria in this model, and an algorithm for minimizing the equilibrium policy loss. So first, we'll start off with our model. As I mentioned before, we can think of the system of treatment allocation over time, where we have a decision maker who's allocating treatments to a population of agents at each time step t and has a capacity constraint that is the same at each time step. The selection criteria beta, we can imagine, is fixed for all time steps t, but the threshold for acceptance is allowed to change over time. So the threshold for acceptance at time t is st. And in our model, we assume that agents are myopic. So at time step t+1, the covariates that they report to the decision maker simply depend on the policy parameters from the previous time step. And this basically results in their strategic behavior, or this affects their strategic behavior and induces a distribution over scores p beta st. And then at time step t+1, because of the decision maker's capacity constraint that they can only accept 1 minus q fraction of agents, the threshold for acceptance is the qth quantile of the score distribution that's induced. So the threshold for acceptance at time step t+1 is q p beta st. Furthermore, we can talk a little bit more about how agents are going to choose what covariates to show to the decision maker. In our model, we assume that agents are heterogeneous in their raw covariates and their ability to modify their covariates. So we can think of their type as consisting of two components, eta and gamma. Eta corresponds to the raw covariates, or the covariates that the agent has prior to responding to the policy. Gamma captures the agent's ability to modify their covariates and basically specifies like how easy it is for them to change their covariates after seeing the policy parameters. This heterogeneity is important to capture because we can imagine that in a population of agents, there may be some people who are more well off, so it's easier for them to respond to changes in the policy, whereas there are some agents that are disadvantaged and they may not have, it may not be as easy for them to modify their covariates in response to a policy. Furthermore, we assume that agents are imperfect and their actions are subject to noise from a multivariate Gaussian distribution. And we can imagine that the agent decides what covariates to show to the decision maker by trading off the cost of modifying their covariates and the reward they expect to receive from getting the treatment. And basically, their utility function will balance these costs. So finally, the covariates that the agent reports the decision maker will basically be a noisy version of their best response, which is the choice of covariates that maximize the expected utility, given whatever their noise distribution is. Now we can talk a little bit about characterizing equilibria of the system. First of all, we can consider the mean field regime, where an infinite number of agents are being considered for the treatment at each time step. So basically, the threshold for acceptance in this setup will evolve through this deterministic fixed point iteration process. And what we can prove in our paper is that there is, when the level of noise in the agent's noise distribution is sufficiently high, there exists a unique equilibrium threshold. And furthermore, we can think about the function that maps policy parameters beta to the equilibrium threshold it induces, and then this mapping is differentiable. Furthermore, we can show that analogous results hold in the finite regime. And basically, as the finite regime is where the number of agents that are considered for treatment at each time step is some finite number n. And basically, in this system, we can see that the threshold for acceptance can be approximated by the mean field equilibrium threshold of the infinite regime. Next, we can talk about how we can minimize the equilibrium policy loss. We take inspiration from machine learning, where our approach to minimizing the equilibrium policy loss basically amounts to estimating a gradient and running gradient descent. The challenge of this approach is that we don't have closed forms for many of the parameters in the gradient, so we'll need to estimate those. And our procedure for estimating the gradient involves applying mean zero perturbations to the policy parameters beta and s to estimate the gradients without disturbing the equilibrium. And basically how this works is that we apply these perturbations to the policy parameters for each agent, and then we observe the treatment assignments and the losses that are incurred for each agent, and then we can run regressions from the perturbations to the outcomes of interest. And this process basically amounts to us being able to estimate gradients via finite differences. And so we can show that the regression coefficients that we estimate in the previous step allow us to estimate different components of the gradient estimator. So we can put them all together and obtain a consistent estimator for the gradient of the equilibrium policy loss. Finally, I'll conclude with a simple experiment that we ran. So we can imagine that we have a population of agents with two-dimensional covariates that consist of two groups. You can think of one group as the gamers, because these agents have low eta, which means they have unfavorable raw covariates, but then they have high ability to modify their first covariate, or they have high gamma 1. In contrast, there are the naturals, which have favorable raw covariates to being accepted, but then they have low gamma, which means low ability to modify their covariates in response to a policy. And we can imagine that in this setup, the decision maker earns a loss of minus eta 1 on agents they accept and 0 otherwise. And our goal is to learn the optimal two-dimensional policy that takes value in the set of unit vectors. And we can see that the naive policy would basically only place weight on the first covariate x1. And this policy is suboptimal because the gamers have high ability to modify their first covariate. And instead, we can imagine that there should be a way to do better, because basically eta 1 and eta 2 are correlated. So if we place a little bit of weight on x2, we should be able to select more naturals. And we can see that basically by using our gradient estimator that I showed earlier, we can learn the optimal equilibrium policy via gradient descent. And this policy actually accepts more naturals compared to the naive policy that basically only places weight on the first covariate. Furthermore, this policy also outperforms the policy that doesn't account for the equilibrium effects of competition. Thanks so much for listening, and yeah, let me know if you have any questions.
Any questions?
Thank you for it. I'm interested when you use your gradient perturbation. Can you be sure the acceptance rate of your
Yeah, that's a really good question. And basically, like, you have to consider So we basically always, when you apply the perturbations, you still accept the qth quant. You set the cutoff to be the qth quantile of whatever your empirical distribution is. And basically, if you consider a sequence of perturbations that gets smaller and smaller as n grows larger and larger, you'll be consistent even with the perturbations. Thanks.
Other questions? I have one question.
Yeah.
First of all, like, it was great to see that you utilized the Frankel and Kartik model. So I didn't get like exactly the structure of the agent's like best response. So can you comment a little bit on that? And I suspect like it's gonna be like a complex behavior. So whether like there's any heuristic that actually approximates.
That's awesome. Yeah. So I didn't get a chance to talk about this, but this is a great question. So basically, you can think like of the agent's behavior as a function of the threshold S. So when the threshold for acceptance is very, very low, what the agents are going to do is basically just sit at their raw covariates. When the threshold is very, very high, it's not useful to the agent to game because there's no chance of them getting accepted. So they'll also sit at their raw covariates. And then when you're in this middle region where there's some hope of the agent getting the acceptance, then they'll start to game a little bit more and basically invest more and more effort into being accepted. And then as that has diminishing returns, they'll start investing less effort, so then their score will go down. And one other thing to note, because I didn't get a chance to talk about this earlier, is the noise distribution that the uncertainty basically in the agent's ability to modify their covariates has an effect as well. Because if the noise is very low, you're going to see that there's kind of discontinuity in the agent's behavior because they know exactly when to invest effort and exactly when to quit. But then as there is more uncertainty in the agent's behavior, then it basically smooths out the best response, which gives us a lot of the nice properties that we need to prove the theorems in our paper. So actually, most of the results of our paper operate in this regime where the best response of the agent is at least continuous. And then even more of the results hold in the regime when the noise is a little bit higher, which allows the score of the best response to be a contraction. Okay. Thanks for the question. Yeah.
Any other last questions? If not, let's thank the speaker again. Let's set up the slides.